those of you not native English speakers. 3 is less than 4. That statement is equivalent to saying that 4 is greater than 3. Right? Those two statements are effectively equivalent. That's ordinary English. Now, the mathematical definition of equivalence relation, and I'll give them here. There's like 3 criteria that have to be satisfied, that your relation has to satisfy. So, an equivalence relation is a particular kind of relation where that relation, that R, or P if you like, put R here, satisfies 3 properties. But before I get into the details, let me give you a feel more. Now, equivalence relations play a major role in pure mathematics. So what's given in this textbook is a bit wishy-washy in comparison to the much more rigorous approach you do in pure math. So let me give you a feel for relations in general of various kinds. Take the relation, the mathematical relation, bigger than. So, if you can something be bigger than itself? So say the something is just x. We'll just call it x. Some object x. So can x be bigger than itself? So can x r? And the relation in this case is bigger than. So can x r x? Can x be bigger than itself? X bigger than x? No, can't. Right? Now, so if x r x, so this is a kind of relation, symbol for relation. So if that is true, then this relation is said to be reflexive. Okay. So I've just given you a counterexample. Greater than doesn't work. So let me try another example where that is reflexive. Another relation that is reflexive. How about equals? Okay. So is 3 equal to 3? Yes. Okay. So equals is a reflexive relation. How about older than? Is x older than x? No. Must be equal. So it's easy to find relations that are non-reflexive. Okay. Now how about symmetric? What does that mean? Well, it means if x r y, if that's true, then this arrowy thing, that means implied. That means you can deduce that, or it follows that, or therefore. Okay. So if x r y, then another then. Y x. So let's find a counterexample. Let's find an example of a relation where that is not true. Let's say Tom is a friend of. So the relation is a friend of. Okay. Tom is a friend of Jim. Now it doesn't follow that Jim's a friend of Tom. I mean the friendship may be one way, right? It's quite possible. Like in a love relationship. Like Tom loves Jane, but does that mean Jane loves Tom? No, not at all. I mean, it's good, right? You've heard the phrase unrequited love, meaning love that is not returned. Okay, so loves is an example of a possible non-symmetric relation. Okay, now let's find one that is strictly true. It has to be reflexive. Let's find a relation. Okay. Let's say Tom is a relation of Jim. Like might be the father, the son, the brother, uncle, what it is, some relation of Y. So Tom is a relation Jim. Well, therefore Jim is a relation of Tom, right? So if Tom's the father of Jim, well then Jim is the son, in other words, a relation of Tom. If Tom's the uncle of Jim, well then Jim is the nephew of Tom, right? So that would be an example. R could be, is a relation of, or for example, X belongs to the same family as Y, right? Or X is a member of the same family as Y. Well, that means that Y belongs to the same family as X. Okay. Right. So that's an example of a symmetric function. Now, a transitive function. Now we're involving like three elements of a set, and this relation, this R, is said to be transitive. Trans across. So if X R Y and Y R Z, then it follows that if it's transitive, that X R Z. I'll give you an example. Friendship. So the relation R would be is a friend of. Okay. So if Alice is a friend of Bob, and Bob is a friend of Chris, it doesn't follow that Alice is a friend of Chris, right? I mean, you should know that from your own experience. You might introduce two people, and you are a friend of both of them. You like them both, so you think, well, maybe now you're B, so you have a friend A and you have a friend C, and you have the thought, maybe I should introduce my two friends A and C. They might get on together because maybe they have something in common, because I'm friendly with both of them. So maybe they have something that I like in both of them, and therefore they have something to share amongst themselves between A and C. Doesn't follow. Maybe, but maybe not. Okay. So is a friend of is quite possibly not transitive. So let's try and find another relation where, of necessity, logically, that relation, that R, has to be transitive. What's a good example? All right. How about is an ancestor of? Well, let's see. So I've got to fluff this up last time I tried. So let me say we have three people, A, B, and C. And we'll start with C this time, because last time I started with A, got into problems. So C. Now let's say like time in generations, human generations, going down this way. So C, let's say C is an ancestor. Hold on. It's a descendant. All right. Well, okay. We'll say answer. So we'll start above. So A here. So with three individuals, right? So three different generations. Let's say. So A is an ancestor of B, right? And B is an ancestor of C. Right? There's a family tree. There's a family link between the three of them. So it follows. So if B is an ancestor of C, and A is an ancestor of B, then A must be an ancestor of C. Follow that reasoning? Okay. So the relation is an ancestor of is transitive. Okay. Now we've done examples that are true and false for a reflexive relation, a symmetric relation, and a transitive relation. Now, in certain cases, some relations satisfy all three of them at the same time. So a relation that is reflexive and symmetric and transitive, all three, that kind of relation is said to be an equivalence relation. Right? So it's a very specialized kind of relation. We're just introducing it now, and equivalence relations, like I said earlier, play a major role in pure mathematics, group theory and ring theory and so on. So the mathematicians like this concept very much. So if you have a relation, and if you want to know if it is an equivalence relation, you have to do 3 tests. 1, 2, 3. You have to test that that relation is reflexive, symmetric, and transitive. And if just one of those or more, if just one of them fails, then that relation, by definition, is not an equivalence relation. Okay? So we'll move on with this a bit more in next session, the next board, because I've run out of the board. If you can see this is the southeast corner, the bottom corner, the end of the 4th session, so the end of the board. So I then have to wipe the whole board, takes quite a long time, and then write out another 4 sessions worth, and then I film. So it's relentless.